Okay, so the next one is we're going to look at the normal reaction force, frictional force, tension, and the last one, upthrust. Let's look at the normal reaction force. So the normal reaction force, firstly, is a force between two surfaces in contact. So they must be touching, okay? Contact forces. Then, another thing to know is, if your surface is like this, the force coming out is perpendicular to the contact surface, where both surfaces are touching. So example, if you look here, we have a box on a table. So maybe we have a gravitational force pulling the box down. That's called our W, the weight of gravitational force we looked at earlier. Then, how come this box doesn't fall through the table? What is preventing it from doing that? In short, it's what we call the normal reaction force. So there is one normal reaction force drawn from the surface of both surfaces there, and this normal reaction force is right angle. And in this case, it's kind of balancing out the weight. That's why the table is not sinking, it's not floating. So it's balanced. And this box is at rest. But what if the table is at an angle, so an inclined plane at some angle theta? Let's draw theta. Thing to remember is there's still weight. Weight is directly down towards the center of the earth. That's W. But what about the normal reaction force? It still has to be perpendicular to the surface, so you kind of draw something like that. Oof, such a curvy line. Imagine that it's straight. And since this box does not fall through the slanted table, that means somehow R must be equal to something about the weight. How you can think of it is this. Now we are tilting the whole system to a little bit at an angle. So our X is kind of like this and our Y is here. So W will have components in the X and Y as shown there. So what you can do is find the component of W, like that. Okay, what is this component? You have to think of, okay, what the angles are. If the inclined angle is theta, means for this triangle, your angle here is also theta, which means the Y component, so-called Y in this case, is W, let's see, adjacent hypotenuse cosine of theta. Meaning, in this case, your Y direction, you have a balance of R equals to W cos theta. Right? So you look back to the original on the left side. That one, everything is just up and down. So W equals to R. But on the right side, if you had an angle, then if your block is not floating, it's not sinking through, then R equals to W cos theta. Next up, the frictional force, cousin of the normal force. Very similar, but a little bit of difference. Let's see what those differences are. Okay, so it's still the force between two surfaces, talking about surfaces, but the direction of the force is now parallel to the contact surface, not perpendicular. So if you have, this is now the box and the table. So you have a box and table, the friction force is going to be either like that or like that. Notice how the arrows are parallel to the surfaces now. One more thing to notice is, just now we said we don't know which direction, right? Is friction this way or this way? We can know if we think about what's the motion of the object. If it's moving to the right, then friction is to the left, okay? If it's the other way, then the friction will change direction. Basically, frictions want to stop the object moving or stop you from flying through the air. One thing to note is that we looked at viscous forces and drag forces, right? So viscous force or drag force is also kind of frictional force, just that it's the contact between the object and the fluid. So the fluid can be you trying to swim in water or you flying through air. Also frictional force, also known as air resistance. But why is there frictional force in the first place? Let's zoom in a bit to this part where the contact surface between two objects is, and we'll see how or why this frictional force exists. So here we have PhET simulation. Oh, my favorites. Chemistry and physics textbook. Frictional force is going to be this way. in this way. Let's see what happens to the molecules in there. Okay, so here's the animation. You see the arrows, one's pointing left and right. Okay, so we have chemistry book and the physics book stacked on top of each other. Notice how the chemistry book is pretty bumpy, very rough surface. So I can smack them down, and there's a normal force there, not shown here. But if I rub them parallel, ooh, notice how the temperature increases. So it's frictional force happening when I rub them together. Let's see what this frictional force does to all these molecules vibrating in there. Gets hotter and hotter and hotter, and eventually, oh my goodness, we just made the chemistry book much smoother. So the friction is actually lesser now because it's not so uneven here. So I can just keep rubbing until I just wreck the chemistry book. Maybe I can start a fire. Look at the temperature on the right. Woo! That's why when you rub hands, it gets hotter and hotter, and that's how people start fires with wood sticks. But yes, that's the animation from FET. Okay, thank you to myself who was showing the animation. So that's frictional force between two surfaces. Why there is because there's bumpiness if you look at the macro, in the very small level, at the atomic level, molecules and all that. So if you want to look back at blocks, let's say I have a string pulling this object, T for tension. So it's moving in that direction. Moving. So where will the friction be? Okay. To draw friction, it's best to split up the table and the surface, draw what we call a free body diagram. Okay. Then we can see exactly what is happening here. So for V. Alright, so as this block is pulling to the right, the table will want to slow it down. This table's rough if you zoom in there, like the molecules we saw just now. So there's going to be a frictional force to the left. You can write it as FR or just F. And that is a little smaller than T. Depends on several factors. Then, well, if you want to think about Newton's third law of pair, table exerts friction on the box. So the box exerts a friction on the table. So the table will experience a friction forward. And these two are Newton's third law force pairs. One question to think about is, what affects how much friction there is? There are two factors to think about. What makes friction larger or smaller? One is related to what we saw in the animation just now. If it's very rough surface, wow, very big friction. So we can say F equals to, in physics we call this the coefficient of friction. It's mu lah. Okay, this is coefficient of friction. Depends on how rough or how smooth the surface is. One more thing is, if your object is just floating, there's very or minimal friction. But if the object is very heavy, so I draw a very big weight here, it's pressing more into the table. So friction is going to be larger. So the last one actually depends on weight and your normal reaction force R. So F, friction force, can be calculated with mu times R. This one is an extra thing. You are not required to find it at A levels because they will just straight away give you the frictional force, let's say 5 Newton. They'll just give it to you. So you don't have to calculate it, but just so you know, there's an equation to calculate the frictional force. Okay, let's see. What if your box is at an angle? Remember, we talk about angles if it's slanted. So first things first, let's say your box is sliding downwards. So you put it there, and then it's like people sliding down the hill, you know. So there's V, and it's sliding down. So if it's moving down, which direction will the friction be? Down means friction should be upwards at the surface. So you draw at the surface. There's a small frictional force there. But wait a second. what's causing the box to slide down in the first place? What's pulling it down? Gravitational force. Remember, objects want to go down to the center of the earth. So there's actually a weight down, this way that's causing the box to have this velocity sliding down. So if it's sliding down, which one should be bigger? Let's see. If you want to calculate the acceleration of the box, I'll say some acceleration. What is the acceleration of this box as it slides down? You have to figure out motion in this direction. You'll need to resolve forces following this tilted axis, like what we looked at earlier, your x and your y. Friction is already in the x-axis, so no problem. But our W, let's draw a triangle right there. So if we are having a slope of some angle theta, this angle here is also theta. Okay, so we're trying to find the component of W here in the new tilted x component. So what is Wx? Think about triangles. Opposite hypotenuse. So, sine. So this W, the force of gravity in the horizontal x direction is W sine theta. Okay, so if I simplify the picture a bit, I will have this way, W sine theta, some force causing the block to slide down. And what's trying to stop it is a frictional force. Yeah. W, sorry, not W, just F. So what is the acceleration of the block? Think about Newton's second law. The acceleration can be found from the net force. So, what's our net force? If acceleration, we say this way, is positive, for convenience, because we don't want to deal with too many negatives. So then, you need to add both forces together. So W sine theta plus, friction's going back. So actually a minus F equals to mass of the block times acceleration. Okay, then from there on, you can solve, and depending on how much info you're given, you can find the acceleration. There we go. So this is for a block sliding downwards. Now, what if the box is sliding upwards on the same plane? Maybe because you, tied a rope there, so you have some tension force pulling it up. Now, for fun, let's just say we're going to draw all the forces for this acceleration, trying to find what it is. Okay, so firstly, you're going to have a weight from the center of mass down. That's some weight. Then you have, what else is there? Normal force, because the block is touching the surface. So you have a normal force. Use black color also. So normal force from the surface. Let's call that R. Then we have frictional force, lastly. Now, if your block is sliding upwards, then you need to have a frictional force in the other direction. So let's draw something there. F. Okay. Now, so many arrows. Whoo. Let's see. What's the inclined angle? Let's just give it a name, theta. So now you need to think about this whole system. Where do you want to be positive? Where do you want to be negative? Lots of forces. We know, let's see, since it's going up, let's say this is our positive x, and this is our positive y. Okay, so our new system is tilted, and everything moving up the slope is positive x. Okay, let's see, let's start off with drawing the component of weight first. Okay, so once again, we need to see what is the component of weight. In the x-axis, Wx will be, we looked at earlier, was opposite hypotenuse, so W sine theta. That's what causes the block to want to slide down in the first place. Gravity is pulling it down. Then we have another one in the y direction. So this one is W cos theta. adjacent hypotenuse. Okay. So if we look at the x direction, that's where the friction is, we'll have a force, tension, going up, and then opposing it is friction. And one more going down. I should draw that. WX. So the x component of gravity also wants to pull the block down the slope. That's why you need such a big tension to pull it up the slope. Okay? So if you want to find the acceleration, just add up all the forces together. F equals to ma. Okay, which one is positive again? Let's see. Everything going up the slope is positive, so friction is negative, weight is negative. So you have T plus minus friction, so minus friction minus weight, x equals to ma. So if you want to sub in the values, you can just put T minus friction minus W sine theta equals to ma. If they want you to find the acceleration, this is an example of how you can think about all the forces and the acceleration of the block. How about in the y direction? Nothing new, still the same thing, okay, like what we did before. In the y direction, you will have two forces only, R and W. So sum of forces equals to ma. We said up is positive, right? So we'll consider the normal reaction force as positive, and then the downwards part of weight as negative. So we will have R plus minus WY equals to MA. So that's for the y direction if they want you to do anything. Okay? So no vertical acceleration in this case. So R is just equal to WY or W cos theta, like what we did before. Okay, so this is a complicated example of how a block can be sliding upwards and how to find the acceleration here. Alright, more friction. What if you're running? We walk all the time. You know, we don't think about the friction. Have you ever wondered why you can move forward when you're walking? Something to do with friction. Okay, this is where you kind of have a mind blown moment a bit. Alright, so look at this human here. This person's running. Take a guess. Where do you think the friction is acting on the person's leg? Which direction is the friction acting on the person's leg? Is it going to be, I'll draw arrows here, is it to the right? Or is it to the left? How? Which direction? To think about this, we need to really zoom in on the leg a bit and separate it from the floor. Okay, let's see. If you stand up, try walk around and feel your leg. If you walk properly, you are actually pushing the floor back. Let me repeat. If you are walking, you're pushing the floor behind you. So that means you are exerting a frictional force backwards on the floor. So this is on the floor by leg. Okay, you are pushing the floor backwards. But what does that got to do with what's the force on your foot? Okay, so think about Newton's third law. Every force will have an equal and opposite reaction, right? So if you are pushing the floor is pushing you forward. So the frictional force on your leg is actually forward where you are running. That's why you can run forward that's why you are propelled forward in the first place. So this is the force on your leg by the floor. If the floor is just smooth ice, you're not going anywhere. There's no friction, the floor's not going to push you forward. Okay, it's kind of mind blown to think about it. But next time you go to gym, you see people running like that. Notice how the conveyor belt is just moving backwards. Because this person is pushing the floor behind him. So pushing. Okay, so next time you go take a walk, think about your leg and the floor and what you're pushing and how you are moving forward. Another challenge question. Now, if you see a car on the road, what are the forces acting on the car? Of course, the car has some weight, so it's going to pull it down. And car's not sinking through the road, so something's going to hold it up, and that is your normal reaction force. Acting on where? You must draw it from the tires. So one there, and another one on the other side. Oh, my arrow disappeared. There we go. So on both tires, you have reaction force. But what about friction? This is a tricky one. It's a two-wheel drive car, by the way. I'll explain a bit what that means. So we need to zoom in a bit when you think of friction. So this car is two-wheel drive, which means the back tire is the one turning for this car to be able to accelerate in the first place. Step on the accelerator, and you accelerate. Okay? So the back wheel is turning. Means very similar to what we're doing with your leg pushing on the road. This tire is going to push the road backwards. So I'll draw a bigger arrow. So because of that, your tire is exerting a frictional force on the road. On road by tire. I think that's how you spell tire. So as a result, Newton's third law pair, if your tire push the road back, then the road will push your tire forward. So that will come there. Oh no, the forces should be the same length. So anyway, this is F on the tire by the road. Just to be fair, let me make this other force down here equally as large because they are equal magnitude, opposite direction. So actually, in real life, what really makes your car go forward is that reaction force. This one, reaction force on your tire. That's what pushes your car forward. Okay, on the wheel that's turning up. But then what about the front wheel? In two-wheel drive car, the front wheel is just chilling. It's not actively turning. So, in that sense, it's like how you would push a box. You're trying to push a box across a surface. You're trying to push the front tire across the surface. So then, the force on the tire is actually backwards a little bit. This is force on front tire, which is just chilling. It's not actively turning because of the engine. Force on tire. So then there will be a reaction friction, which is a little bit by the tire on the road. Wow, this is very strange. See how the friction is pointing in different direction. Okay, so friction will push your car on the back tire. Friction will push your car forward. The front tire is just dragging. It's trying, so the front tire is trying to pull the road forward, and the road is exerting a backwards force on your front tire. Take some time to digest this picture a bit, okay? Two-wheel drives, pause the video, look at it, ask any questions in the questions channel before we go to the next last bit of this video. So two-wheel drives, we looked at just now. You got friction that your tire is exerting on the road. It's trying to push back the road because the back tire is turning. So it push. Friction on road. And as a result, Newton's third law reaction pair, the road is pushing your car forward with a friction force on road. So in this situation, the only thing different is a four-wheel drive. So four-wheel drives, okay, this car probably doesn't have a four-wheel drive, but four-wheel drive means the engine is going to make both tires turn. So both tires are actively turning. Both tires are trying to push friction backwards. So then you have something like this. Pushing friction on road by tire. Tire trying to push the road back. In return, the road is pushing the tire forward. F on. Why I say road? Tire. F on the tire. So you see now, there is much less backwards friction force. In fact, almost none. Which is why four-wheel drive cars are very powerful in all kinds of terrains. Which is why four-wheel drive, they go through mud. Like, okay, you know how four-wheel drive looks like? They look basically like this. They have a back boot, and then they have like that. That's How's okay, they have reinforcement frames. This is how a four-wheel drive look like. They are used for off-road, go in the forest, go in like a jeep like that, go in the forest, go in the mud, go exploring. Four-wheel drives are very powerful because of this reason, because lots of power to move forward, because all four wheels are actively pushing the road behind them.